Let's have a look at our third case of projectiles where they're launched at an angle, like our second case, and it lands at a different height, like our first case. So this is a much more complex projectile problem, but we still go about it the same way. So in this case, we've got an object being launched at an angle vertically, and it lands either below our initial point or above our initial point up here. So this is in contrast with the second case where it lands at the same height. Now there are a few interesting observations to make before we look at a problem. First of all, the displacement in the y direction will either be positive, so above the start point up here, or negative, it'll be below the start point here, because we say that by convention, if it's moved up, it's positive, if it's moved down, it's negative. Secondly, we say that it's non-symmetrical motion through that parabola. So in our second case, we said that we had an object moving through this parabola. We'll notice if we put a line halfway down, we get this symmetrical movement. And that means the angle of launch will equal the angle of landing. That's not the case with our one here. We'll notice that the movement on the left-hand side is not equal to the movement on the right-hand side, and that tells us that we will, first of all, have different times from here to here and here to here. We'll also have different initial and final velocities, and we'll have different angles of launch and landing. So, despite these differences, we still go about solving these problems in the same way. First of all, we've got to split our initial velocity into its two components, initial velocity in the x direction, initial velocity in the y direction. But we also need to make adjustments for this change in the displacement in the y direction. So let's look at how we do this through a problem. Let's say that a ball is launched at a height of 1 metre from the ground, and it's launched at 20 metres per second at an angle of 37 degrees. We want to find three things. First of all, the time aloft, second of all, the maximum height, and third of all, the range that the object has moved, or the ball has moved. So the same way that we went through with case number 2, we need to find our x and y components first. So I always start with a diagram, and then I can see where my information is. So we've got our ball being launched 1 metre above the ground, where it's going to land. It's being launched with an initial velocity of 20 metres per second at an angle of 37 degrees. So to find our x component for our velocity, we're going to get initial velocity times the cosine of the angle, so 20 cos 37, which gives us 16 metres per second in the x direction. Similarly, for our y direction, we're going to get initial velocity times sine theta this time, sub in our values, and we get a velocity in the y direction of 12 metres per second. So we can start writing some components down here. First of all, in the horizontal direction, we don't know the range, so that's unknown. We know our initial velocity at 16 metres per second and our final velocity at 16 metres per second because we have zero acceleration in the horizontal direction on that object. We also don't know the time that the object is aloft. In the vertical direction, we've got two parts. There's the part where we're halfway up, and there's the part where the object has landed. So in the vertical direction, our displacement up to this point here is unknown, but our final displacement is going to be minus 1 metre. And we say that it's -1 because we've picked the positive direction as being upwards. Our initial velocity is going to be 12 in the vertical direction. Our final velocity at the top is going to be 0, and it's unknown at the landing point here. Then obviously our acceleration is going to be minus 9.8 metres per second squared, because it's going to be in the negative direction. And once again, we don't know the time that our object is going to be aloft. So, first question asks, for how long is this object aloft? Well, we're going to do this in the vertical direction, so we've got our vertical components of our final, our landing point. So we've got -1 metre, Our acceleration is minus 9.8 meters per second squared. Initial velocity in the y direction is going to be 12 meters per second, and our unknown is our time aloft. So we use s equals ut plus a half at squared. Unlike the second case where we had 0 here, this time we've got our displacement as minus 1. So this time we'll have to go through to solve our quadratic, and we do that by using minus b plus or minus the square root of b squared minus 4ac over 2a, which is how we solve complex quadratics. And we get two values for t, one of 2.3 and one of minus 0.081. So obviously the time taken must be a positive value. This negative value would indicate that it was before the launch of the object. So our value here for the time aloft will be 2.53 seconds. Now part B asks for the maximum height. So we're looking at vertical components only here. Our S at our apex is unknown. Our T at this point is also unknown. Even though the total time was 2.53 seconds, we don't know the time that it took to get to the top of the apex. So we've got an initial velocity. Our final velocity will be 0 meters per second at the top, because it stops moving just before it keeps moving down, and our acceleration due to gravity is obviously minus 9.8 meters per second squared. So using v squared minus u squared equals 2as, we now substitute all of our values in for s, and we find that it climbs to a height of 7.35 meters. You'll notice that's a positive value because in our initial question or our initial diagram showed us that we had 1 meter there, so the object is climbing to 7.35 meters right at that apex. And our third part asks for the range of the object in the x direction. So our unknown is in the horizontal direction, total time is 2.53 seconds, initial and final velocities are the same at 16 meters per second, and our acceleration is 0 in the x direction. So we use s equals ut plus a half at squared, where we substitute our values in. Notice how we haven't got anything in this component because our a is equal to 0, and we find our final range is 40.5 meters. So slightly more complex, but still very doable in exactly the same way as we did case number 1 and case number 2.